study our colloquium today. So thanks so much for coming, and this is one of the few physical colloquium study this year. And we have a great pleasure to have the Yu-Heng Lin, Yu-Heng from the University of Minnesota. And actually also graduated from Minnesota about 8 years ago. And he's now a PhD student, and he's working with Claudia Scaler, and she's an expert of the spatially HeII galaxy survey, and also many people now are very interesting on this the issue about the reionization of the universe. And Yu-Heng now will give a talk about the powerful Type II QSO identified by broadband detection from diamond alpha emission. So let's welcome Yu-Heng.
Okay, so should I close the light in the front?
It's complicated.
It is. It's already closed. Okay, we got this. All right, thank you. Today I'm going to talk about powerful Type II QSO identified by the broadband detections of diamond alpha emission. And before I start, I realize I might have to, it might be offensive, but I might have to introduce quickly about what's a Type I and Type II QSO. So QSO means a quasi-stellar object, which means that they originally thought it was a star, but because of resolving images, and then it turns out they realized it's a powerful supermassive black hole emission from the center of galaxy. So I'm going to pronounce QSO as QSO most of the time because given the time that they realized quasars and QSO or AGNs are basically the same type of galaxy, a little bit that quasar is a radial source and QSO doesn't have to be a radial source. AGN usually means the center of the supermassive black hole, the nuclear region, or the low luminosity objects, but the terminology may be mixing around, hopefully. I'm just going to talk about supermassive black hole thing. Okay. And I'm from University of Minnesota, which is not necessarily a famous place in Taiwan. So small introductions. Minnesota is a blue state, but the map happens to be red. It's on very north of US, besides Lake Superior. And during the summer, we have like beautiful nature, green grass, and then during the winter, we have white grass besides the lake, and the Lake Superior will be frozen on the side. But it's still a nice place, although that this picture was taken 2 weeks ago, that Taiwan was in afternoon 8 p.m. and it was 20 degrees, and Minnesota on the morning was minus 20 degrees. In my very short PhD career, I have experienced 2 times that the Fahrenheit and Celsius are the same number, which is negative 40. Only happens a few times a day, few times a year. Okay, so this is my outline. I'm going to introduce my galaxy. It's called S8220. S82 is from the Stripe, SDSS-Stripe 82, and 20 is simply just an ID. And I'm going to talk about the photometry and spectroscopy data, and then because of the way we find it, we have to distinguish the galaxy, to see whether it's a star-forming galaxy or an AGN. So we're going to introduce for the photonionization model to distinguish the 2 types of objects. And then later on, I will introduce if there's any similar objects in the previous study, and then talk about our conclusion about this galaxy study. So at the beginning, our interest is actually trying to find the high redshift, low metallicity galaxy. So then we start to look for, in an image, start to look for faint objects that have that have exceeding G-band flux. And the reason for this is that for star-forming galaxy, we might have a stronger ionizing spectrum, which produce large Lyman alpha flux, or say large Lyman alpha equilibrium width. And in redshift of 2 to 4, which is the cosmic time where most of the galaxy are in a high star formation phase, we will see strong Lyman alpha. If it's really a star-forming galaxy, the Lyman alpha will be outstained compared with other band. So then we will see that the G band is brighter than other band, although the entire galaxy might be faint. So that's the criteria for star-forming galaxies. In high redshift. And so then we find this guy who has, or a girl, who has a magnitude of G band of 22.17. And just a reminder, the higher number it is, the fainter it is. And then R band is 22.87 before the correction. And then before the correction means that we haven't removed the emission yet. So this is the observed number. And this faint object will not be considered as a quasar in the, say, Bose pipeline. And then we have no detections in Ys, W3 and W4, which corresponding to the observed frame of 12 micron and 22 micron. Redshift, because I have spectrum, so I know the redshift of the object, but it's going to be a redshift of about 5 micron. So we have this object, and then before, like, say, having this object, then you consider maybe this is a low metallicity star formation galaxy, a star forming galaxy candidate, and then you need to go into a follow-up spectrum to see what's inside the galaxy. So then we have several observations on this galaxy. We have polymer data at the beginning, and then SOT, which is South Africa Large Telescope, and then at the end we have MOSE LBT. The rest of the data in this paper, in this presentation, most of the spectrum data are from MOSE LBT because it's the best instrument I have. And then for photometry data, we have SDSS, IRAC, and WISE, which is from 3.4 micron to 22 micron. But basically observe optical region to the near infrared. And the spectrum shows us this way, which then you can, by the feature of the emission line, you identify what emission line this galaxy are presenting. Most easy to identify as the Lyman alpha because of the symmetry and the width. And then once you have the Lyman alpha, you basically know what's the redshift, and then you can guess or identify other rest of the emission line, which I'm going to name a few that's very important. Besides the Lyman alpha, there will be nitrogen 5, and then typically in UV, we're looking for C4 1550. It's a doublet, means there's two lines that are unresolved and it looks like a single line, but hopefully you can see there's a double peak here. And then we have helium-2 1640 06 and C3 1909, which is also a doublet, but we won't see a single peak. And then most importantly, or say interestingly, we saw oxygen 6 1034. It's a doublet again, so 1032 and 1038. And I introduce like what's important about this emission on later, but then we already can see that 066 is a large number, which you need to lose 5 electrons to produce 06 emission. So that's not an easy thing to achieve. It's a rare emission line to observe, basically. And then we can, since we have the broadband images, so then you can put on the Western wavelength to see the spectrum energy distribution for our galaxy. And for those which in the image we do not detect the images, the objects, we put an upper limit for 3 sigma upper limit. And then you can see that this is mu luminosity times the frequency, and then kick the log, versus the reference wavelength on the bottom plotted in log scale. You can see that our reference UV spectrum is very blue, which means it's very sleek. And then we have IRAC, which represents to reference 1 micron. And then the near infrared will be the WISE W3 and W4. And then I'm plotting the template of star-forming galaxy as this brown color, and then type 1 quasar, which means you directly observe the quasar absorption accretion disk. So type 1 quasar versus type 2 quasar, where the accretion disk is obscured. You cannot directly observe the supermassive black hole accretion disk, but then you can see the associated emission lines and the infrared. So that's why the infrared is higher. I'm normalizing to IREC 3.6 and 4.5 micron just because it's the highest, longest wavelength that I have in this galaxy. And then you compare the shape, getting the idea of what kind of object it might be, but this is not necessarily the way to identify the type of galaxy. For example, I can also normalize to Raspberry UV. Say, if my spectrum is more similar to a type 2 quasar, then if I normalize to the UV, we can decide that, oh, we are actually missing the infrared energy, things like that. So we need more information to decide what type of object the galaxy is. Especially, say, we have the spectrum, and then we have the flux. Lyman alpha equals to 3.5 times 10 to the 44 ergs per second. That's a huge number. For star-forming galaxy, usually 10 to the 43 is the upper limit for observed star-forming galaxy for Lyman alpha. And then we also see the 06 emission 1032 and 1038, which requires very high ionizing energy, as high as 113.9 eV, which means one single photon has to be about 114 eV in order to ionize from O5 plus to O6 plus. And then once the electron recombined to the atom, it releases this doublet. So at some moment, you must have such high energy photons in the galaxy, which for stars, even the most massive star, it's hard to produce enough amount of such high energy photons. So that's why the 06 emission line is very important in this spectrum, since we start with a survey to search for star-forming galaxy and end up seeing 06 emission. And then next we have the width of the emission line, which is around 700 kilometers per second. For high redshift galaxy like Z larger than 2, the full-width height maximum for star-forming galaxy can get as high as 500, 600, but then 700 is right on the edge of, it's a little bit high, but not too high for AGN, because for type 1 quasar, you might have broken emission line, which the full-width height maximum will be 3,000 or even higher, and for narrow line, it's about 1,000, smaller than 1,000. And then we have very large equivalent width for Lyman alpha and C4, both estimatedly larger than 200 micron. Again, numbers for type 1 quasar, it's single-digit number, and then for type 2 quasar, it's like about 50. Okay. And these numbers also, just fun fact, high equivalent with Lyman alpha is one of the signature for searching for top 3 stars. So that's why it brings a very strong interest for studying this galaxy. And then next, since we are using a star-forming galaxy survey to find an interesting object, which is most likely a type 2 quasar, so you wanted to throw in a photonionization model to distinguish whether this object is a star-forming galaxy or an AGN. And again, this is one of the examples, but then when you apply this kind of survey to the larger area, you're going to get a lot of galaxy that's right in between. So you wanted to have a systematic way to distinguish the two kinds of objects. And one of the famous example for using this model is a BPT diagram in optical, that you look at the O3 and nitrogen 2 versus the hydrogen line. Since the AGN can produce stronger energy photons, so then you can have a higher ionizing emission than the star-forming galaxy. So that's why the AGN distribution is more on the top of the figure. And then in UV spectrum, you can also try to use emission line ratio to distinguish the south-forming galaxy and AGN. And so far, there's no such like classic famous diagnostic diagram to distinguish south-forming galaxy and AGN in UV. But then overall, people like to use helium-2 because the helium-2 ionizing energy is 54.4 eV, which is right on the edge of like O star, the largest star. The temperature is about the edge for corresponding to 55 eV. So anything divided by helium-2 will separate south-forming galaxy and AGN pretty well. So that's we're going to see a lot of C4 over helium-2 or C3 over helium-2. And this model is produced by one of our collaborators, Anna Filtri, in 2016. So that's also interesting to think that BPT diagram are studied since about like 1990s-ish, and people started to study UV at like 2016. And then another type of diagnostic from the clouding model or photonionization model is using the equivalent with plus the line ratio. Equivalent with is the emission line flux divided by the continuum level. So then the equivalent with also tells you how bright the emission line is relatively to the system size. And for AGN, it usually can produce stronger emission line than the south-forming galaxy. And then again, you can see we're using C4 over helium-2 here. Okay. So this is the ionizing spectrum of the two, comparing south-forming galaxy and AGN for the ionizing spectrum. As you can see that for lower metallicity south-forming galaxy, it can produce slightly stronger, harder photons ionizing spectrum than the south-forming galaxy with this is 0.2 stellar metallicity, higher metallicity galaxy. So it can produce stronger photons with lower metallicity. But then compared with supermassive black hole, then it's very hard for a star to produce like 80 eV or 50 eV, where helium-2 is like on the edge, that the star cannot produce so much helium-2, but then AGN can do that. So then next, we can use the photonionization model to produce the emission line of south-forming galaxy, and then we plug into we take out what the stars can produce, what's the flux of emission that the star can produce, and then put it into diagram. And then we do the same for AGN, put in a diagram. Then the rest of the test, you measure your galaxy, you get the line ratio, throw it into the plot, then you know what it is. That's the idea. So then for stars, we have to apply a closed geometry, which means all the gas are covering the stars. And then we use the Chandra IMF, the initial mass function, where the mass is up to 100 stellar mass, and then we use carbon to oxygen abundance equals to the solar abundance. And then we have, for south-forming galaxy, we have a constant south formation rate and the age at 100 million years. And then our model have the ionizing parameter from -1 to 10 to the -1 to 10 to the -4. Gas density for the H2 region is 10 to the 2 to 10 to the 3. These are just like typical number for modeling the star formation galaxy. Although I would say 100 solar mass might be arguable. Like people start to explore 300 or like more interesting, like heavy top IMF, things like that. But so far, these are just like standard way to model south-forming galaxy. And then we look at the metallicity from 1 solar metallicity to have 0.01 and then very low metallicity. Then we get the result where you can see that the lower so the blue is the lowest metallicity and the red have the highest 2 solar metallicity. And then you can see that the lower the metallicity is, our result shows that it's going to produce more nitrogen, more helium-2 than carbon-4. So the ratio is getting lower because you got stronger photons and then produce more helium-2. So it goes down. And then because the abundance, that nitrogen is a secondary element, so then the lower the metallicity you are, you're actually getting less and less nitrogen, and then the ratio of nitrogen over C4 will be smaller. Okay.
Sorry, I'm just curious. What caused the sequence? What's the parameter?
Oh, these parameters are the ionizing parameter.
Okay.
So meaning that how much ionizing photon you have compared with the atoms numbers or gas density. And then you do the same thing for AGN, but then the big difference is that AGN's narrow line regime, by the way, because if it's broad line regime, you can just see and then tell like, oh, 3,000 fluid have maximum. Narrow broad line AGN, case closed. But then for narrow line regime, it's a little bit like ambiguous. So then you have to do the model and tell the difference. And for the difference between star-forming galaxy and AGN is that the covering factor for AGN narrow line regime is small. So then you use an open geometry, which means the gas is not like surrounding the ionizing source. It's only covered a little bit. The covering factor is very low. So then the photons will interact or not interact with the gas and then escape easily. And then the ionizing spectrum is also different, which the main difference for UV is F mu or S mu. The flux density for frequency is proportional to the frequency to the power law alpha, which our alpha is minus 1.4. That's the best feeding from the data. But then again, the model exploration will be from -1 to -2. And then ionizing parameter, gas density, those are just standard numbers studying from the emission line from the previous studies. And then we use the same set of abundance and metallicity to compare the two types of population. And with the same scale and the same axis, C4 over helium-2 and nitrogen-5 over C4, we're going to see that since the Asian population can produce more helium-2, then the whole population goes down. And then again, the abundance actually affects nitrogen emission line flux. So then the lower metallicity it is, then the lower nitrogen-5 it will be. So then that's where the population will be located. And then I also just plot some studies of high redshift Type II QSO. Then the population, the observed numbers usually populate here on the top of the population, where I would say on the top the ionizing parameter is about 10 to the -1, and then the lower the ionizing parameter is, then the lower it gets. And then the other factor that you can also consider is high velocity radiative shock wave shocks. So those shocks are coming from either from AGN with the outflow, then you have the density gradient and produce shocks, or from supernova explosion in the star-forming galaxy. So basically, either star-forming galaxy and AGN shocks are going to be a contributor for emission lines. And then there's no like good model to distinguish between like shocks or AGN. So then it's always, every time you see emission from AGN, you have to consider how much of them are coming from shocks. And also for star-forming galaxy, seeing a star-forming galaxy, some of the emission line might come from shocks. And maybe those 06 are coming from the remaining of the supernova explosion shocks. So then that's why we also look at how much emission line and what's the emission line ratio of shocks. And the model was calculated from mapping 5, shocks emission line model. And the main factor for shock's energy is shock velocity, which we are looking for 100 kilometers per second to 1,000. And that's going to be a fact for the shock's energy input. The higher velocity it is, then the higher energy you have. And then also the metallicity, where I'm going to plot 0.001 half solar metallicity, 1 solar metallicity. But that's because that already covers all the model that I need to consider. Otherwise, in this paper, they have more metallicity in the library. And then pre-shock density and magnetic field is an important factor in shock's model, but when you divide each other in the emission line ratio, then it becomes like not a big deal. So pre-shock density and shock and magnetic field, I simply just select some number because it doesn't affect the emission line ratio model. And this is the result of the high velocity radiative shock in the emission line plot, where you can see this increasing lines increase with the shock velocity. And this turning around is actually a phase transition between the ionizing species, where this turn means that you are running out of C2+, and all the carbon are ionizing in the next level, so then start to increase the C4 photons, things like that, and then just keep rotating. But the most valuable part is when you combine the three population or three models together. You have the star-forming galaxy on the most top because it couldn't produce as high helium-2 emission line. And then you have the shocks in the middle and the AGN in the bottom. So once we plot this plot and then fill in our galaxy, the measurement of our galaxy is the black dot. And then you would say, aha, it's the emission lines are from the shock wave. But not necessary, because first of all, we don't know how much emission flux can the shocks produce. And secondly, our result could be just a combination of star-forming galaxy and the AGN, and then they just like somehow add together, take the average, and then result in the middle. And then we have more photonionization diagnostic, which will just perfectly place SAU-20 right in the middle, where I would say this is very close. But somehow in the middle, such that it's very hard to just say this is either a star-forming galaxy or shocks, result of shocks or AGN. And this kind of things happen again and again until you see like 06 emission line where the star simply cannot produce any strong 06 emissions. So then we're left with either it's a result of shocks or AGN. And then, so until then, I would say the best guess for SAU-20 is a highly obscured quasar. The reason why it's a quasar is because the presenting of 06 and also the full half maximum for 700 kilometers per second. And for highly obscured, it means it has a very high equivalent width, such that the continuum is very weak, and then so that's why it's highly obscured. But besides being a highly obscured quasar, there's something that's interesting. First of all, we see in the diagnostic that SAU-20 has a higher C4 over helium-2 ratio. And then secondly, in the spectrum, you can see that the shape of SAU-20 is, it doesn't look neither like Type I quasar or Type II quasar. And then thirdly, a lot of quasar would have their UV emission absorbed by dust and then re-emit into near infrared or mid-infrared. But then we have no detections higher than 2 micron. So then if this is a quasar, then where does the energy, like it's a quasar where we have very faint UV, so we can guess that the UV are absorbed and then re-emit to the infrared. But then in that case, we should see the infrared where we don't. And then, so that's like the special thing about SAU-20. And again, the broadband is very faint, such that it won't be considered as a quasar in the survey. So you cannot find this type of object in the catalog, and order comparison might not be reasonable to compare with SAU-20 simply just because it belongs to a different scale in terms of luminosity. So then, firstly, if we wanted to compare this object, we can look for what's similar object for high redshift Type II quasar. And then in the Alexandra 2013, they select from the spectrum in SDSS, they select high Lyman alpha C4 emission galaxy from a mother sample of 100,000 objects. And then within that 100,000 objects, they look for Lyman alpha and see for emission larger than 5 sigma, resulting in 80,000 objects. And then later on, they look, next step, they look for the narrow line, full wave maximum smaller than 2,000 kilometers per second, then resulted in 2,500 objects. And then later on, they look by the line, looking for a weak continuum and no broadband absorption features, and then resulting in 450 objects. Within this 450, sometimes they will see a little bit broad base in the emission line, which might be just faint type 1 object. So then they pick within this like 450 objects, they pick about 150 type 2 AGN candidates, and then resulting in this type of spectrum, which is very similar to our object. We have O6, Lyman alpha, nitrogen 5, C4, helium 2. So also just wanted to say, maybe if you are an expert of type 2 quasar, you see a spectrum, you're going to say, this is type 2 quasar, no problem. But the type 2 quasars are so rare in high redshift, such that even we search for the quasar within, how much is that? 100K, 100,000 objects, you only find 150 high redshift type 2 quasar candidates. And then, so it's a rare object already. And then the follow-up spectrum for these type 2 quasar candidates, they still see broad Baromine, like H alpha or H beta, broad Baromine emission. So then they conclude that these objects are only just moderately obscure AGN, means it's partially obscure only. And it's not like perfect type 2 fully obscured quasar. And then another similar object is most luminous Lyman alpha star-forming galaxy ever observed, published in 2020 in, I think, September, that report Lyman alpha emitter that has Lyman alpha luminosity up to 10 to the 44, and this is the spectrum in the papers. And they have SED feeding concluding that stellar mass is 10 to the 10. And the reason why they think this is a quasar is that they have associated absorption lines that performs piecing profile, which is a common feature in star-forming galaxy. And also it's very blue in UV, just like our galaxy, which is not common in type 1 or type 2 or type 1 quasar. So then they conclude that it's a low luminosity galaxy, and in order to let Lyman alpha escape out to the from the galaxy, it has to be a dust pool galaxy. Otherwise, Lyman alpha scatter easily and then absorbed by dust. And then we plot the similar object SED of A13 samples and our galaxy. You can directly see the difference between A13 samples and our galaxy. There's a gap. This is a physical scale, like all the numbers out there, direct luminosity. And you can see that our galaxy have very blue UV reference, and then also there's a gap between the reference 1 micron between this population and our galaxy. So basically, our galaxy have way bluer UV spectrum, and also have a smaller scale in 1 micron reference. And then when you throw into the photonionization model, you see that A13 samples, all those type 2 quasar candidates, basically are out of the range of reach for AGN. So they've also placed right in the middle, where these models are already well tested by other populations of type 2 quasar. So I would say A13 type 2 quasar are very similar to S8220 in the photoionization model. And then here's just more models that putting together, they belong to the same population. And this is, in the previous year I said that there's a line ratio versus equivalent width, where they distinguish, by experience, they distinguish the AGN and star-forming galaxy and the composite. Composite means it's a mixing or a combination of AGN and star-forming galaxy. Then we can see that AGN could be a composite galaxy looking at the C4, or it can be AGN more closer to AGN by looking at the C3. And this is the most extremely UV luminous galaxy, which is the southern galaxy that I just showed. And it's closer to southern galaxy region. And they do not study on the C4 because the C4 are strongly affected by the PCM profile, so it's not available for this kind of diagnostic. And then just a little bit, wanted to compare, although the line ratio is very similar for A13 and S80-20 megagalaxies, you can still see that I'm plotting the continuum around Lyman alpha versus the Lyman alpha luminosity, that this is, the slope is basically like the higher equivalent width will be located here and lower equivalent width will be on the bottom side. And you can see there's a trait that most of the type 2 quasar candidates have equivalent width around 50 to 100 in this population. But then there's a small population of type 2 quasar candidate that has very high Lyman alpha equivalent width. So these population could be just more obscure than the other because these population are concluded to be modestly obscure quasar. And then the EUV LG1, the sophomore galaxy, happens to be the lowest equivalent width because the stellar population can produce strong UV-based continuum, which will lower the equivalent width. And then I would say, like these, not I would say, like I know that these population will be representative the lower continuum population. And then you can see that this is a histogram of the equivalent width of these samples that most of the galaxies are located here, but then there will be a small population that have fainter UV and resulting in a larger equivalent width. And then the equivalent width will be a key point in our survey to find like these type of objects. So then the scenario to explain the weird thing in S80-20 could be the following three. First, which is the same scenario to explain the A13, that they said it's a modestly obscure quasar, meaning that you see some features of type 1 and some features of type 2. And since the C4 over here in type 1 quasar is observed as high as 50, so then you can, by mixing the spectrum, you can hopefully bring up the C4 over here in 2. That's one of the scenario where then you would require 55% of C4 emission from the type 1 spectrum to bring the C4 over here to up. And it is very hard for S80-20 to do so because our emission line flux are calculated by simply integrate the emission line flux within plus minus 1,000 kilometers per second, which means the line width for the C4 doublet is about only 800, and that belongs to the narrow line region. Then you will need 55% of the narrow line actually coming from the broad line. If they are from the broad line, then you should also see the broad line emissions outside this range. So then if you're seeing a very narrow line, you cannot expect that 50% or more than that are coming from the broad line region. And then second scenario is just like the EUV, the southern galaxy, that what we are seeing is a type 2 quasar plus a south-forming galaxy. And then from that, we have the example that some of the south-forming galaxy can be as bright, Lyman alpha can be as bright as 10 to the 44. And in the case, the stellar population is going to produce strong UV continuum, which our UV is very faint. So then, in that case, we can make an assumption that all the UV are coming from the stars, and then we mix this spectrum with the type 2 ASIAA model to perform SED feeding. And the best result come out to be that our south-forming galaxy have south-forming rate about 50, and the stellar mass is about 10 to the 10. It's not like a crazy number, and then most importantly, the obscure level will be AV about 27, which E of B minus V will be about 9. So then, in this case, we would say that the type 2 quasar plus the star scenario is going to be a better fitting in this, a better story for this type 2 quasar. But then at the end of the day, there's no way that we can separate how much emissions are from the shots, because the shots can simply reproduce all the emission line ratio. And then, so like we might have a wrong understanding on the scale of the galaxy simply because we don't know how much of the emission line can be contributed from the shots. And then it's still like a huge mystery that even though we are trying to reduce the scale of the AGN such that it won't have a strong infrared emission, there's no way in either three models that we can explain why we are missing the infrared detections. So the conclusion. First of all, we discover luminous Lyman alpha S80-20 by the broadband imaging from the exceeding of G band. So when the G band is brighter than other bands, we know that it might be a candidate for redshift of 2 to 4 that has strong Lyman alpha emission. And this is a good method to discover self-forming galaxy. However, in this survey, we discover a high redshift type 2 quasar, and we find that this is a highly obscure quasar with O6 emission and large equivalent with for Lyman alpha and C4. And this galaxy is, even though type 2 quasar in high redshift is already very rare, this is even rare that it has a higher C4 over helium-2 ratio than the typical type 2 quasar, and it has a bluer UV spectrum than all the quasar that is already similar in C4 over helium-2 ratio. They still have a very bluer UV spectrum. And then, given that the Lyman alpha is so bright that intrinsically the supermassive black hole can be very bright but highly obscured, in that case we should see remit strong infrared, but then the infrared is very faint. And all these you can just throw it into shocks. But besides that, the best explanation is that we have a highly obscure quasar and a star-forming galaxy, which the star-forming galaxy has to produce strong Lyman alpha, resulting in the dust pool. So that the whole picture of the galaxy is that we have a dust pool host galaxy and a very highly obscure nuclei, which have a lot of dust. And physically, it doesn't make sense, but then it turns out to be the best explained model. And it is very weird. I'm sharing this galaxy, hoping that we have an expert here to tell me maybe I'm wrong or what's a better scenario. But then before that, I'm going to publish this. Thank you.
Any question? Is it?
Or either way, sort of minus some information. It seems like you've gotten this from a survey. Sort of you do a census and see how many you found on this sort of profile selected event. Right? Is that right?
Yeah. So you can download the Stripe 82 images. So you can download the Stripe 82 images and then compare it with the different band images and then see the location.
The question is this the only source you found? I mean, I'm wondering about source density for these kind of objects.
So you can find like a few of these kind of sources, and then you apply a follow-up spectrum. Most of them are star-forming galaxy, and only this guy shows O6 emission, which is like, oh, that's not going to be a star-forming galaxy, but what's going on? So yeah, and we target the source that's fainter, so that it's not a quasar, and then it's still a quasar. So yeah. Also, like the wise infrared is one of the way to throw away the quasar because like they remain in infrared. So like you can take them away to select the star-forming galaxy.
Right. Except this redshift, WISE is not really constrained in terms of plus emission.
Sorry.
At this redshift, high redshift, not 2 to 4. I guess unless it's really luminous, WISE is not really constrained in terms of dust mass and dust luminosity, because the upper bound is so high, I think. So I guess what I'm getting is that non-detection wise doesn't mean that it's not dusty.
I would say it's just a pure guess. So because from the spectrum we see that we would guess this is a type II quasar.
Right.
And then in that case, seeing the UV in that normalized into the UV, then you should get a higher infrared, and that's all. Right. And secondly, we see the similar object, A13 samples, and they have similar levels of UV emissions, and then many of them do detect it in the wise. Not all of them, not all. Like the blue lines are the one that I put in the limit, which happens to be in a lower scale. Like you see, kind of like a level things, but then there's still a gap between the near infrared. So I do not know what's going to happen in W3 and W4. Say if I write a proposal and trying to ask for infrared spectrum, I don't know where it's going to locate. But then this is 3 sigma limit where if it has the same level of UV, then like the seesaw effect, then we should expect to see similar spectrum. Sorry, similar level of infrared. That's a
radio then suggest doing outbound observations.
Yeah, then I have to follow up. We have other like limit that I did not show, but they're just not detected.
Like Herschel stuff, I suppose.
Yeah, Herschel is not detected, but the Herschel is not like super deep for this type of object. So yeah, one of my potential proposal is going to write for the infrared, which my advisor thinks this is a good proposal. I'm not super sure. I will do it, but yeah.
Any other question?
Yes.
Well,
so when you do the SCD fitting, do you remove the
emission
flux?
Yeah. So I forget to mention that when I'm showing this plot, this is an observed emission line directly, and then we remove Lyman alpha, all the emission line actually. Remove Lyman alpha 06, and then it drops down to the white spot. And that's the point where we throw it into the SED feeding.
But for the spectroscopy, it's long slit.
Yeah, it's long slit. So it probably doesn't include all the emission, and we actually may have to remove even more emission lines. That's one of the points that keep in mind. But then in that case, I would say it just make, where is the SED? Okay. So then the point potentially can be even going lower. But then, yeah, that's one of the points that.
That's the point I'm going to make. It looks like the broadband flux is mainly contributed by the line.
By the
line, not the
by the line, not the continuum. Yeah, it could be one of the how do I see this? Let's say we have the 06 emissions that shows that the intrinsic accretion disk should be very powerful. Otherwise, the 06 is almost as luminous as the C4. And given that we should have also a strong UV continuum, but then once we remove the emission line, we end up with a very faint UV continuum. And that concludes to be a very obscure quasar. But then, if that's the case, then it doesn't explain the slope of the UV if we have a very obscure quasar. And then also you might want to normalize the template according to the UV because it's detect, and then we are missing an infrared. So I'm running into a dilemma where if I wanted to capture this feature, then I lose some part of the other, and if I capture this, I'm losing the UV side.
So it looks like it would be helpful if you can do some high spatial resolution optical IFU to see where exactly the line comes from and exactly what's the continuum flux.
Like before this talk, when we were coming from lunch, my advisor just wrote an email asking me to write a HST proposal for what you just said. And HST proposal, but I'm not super sure. IFU spectrum looking at the restaurant UV optical versus the continuum versus Lyman alpha to see if we have a Lyman alpha halo. That's one of the possibilities. And the other thing is that the Type II quasar may produce stronger alpha scale than the South Mean galaxy. That could be distinguished in the IFU. With this data, then this is how much story I can say.
Good. Any other questions?
Yes.
Could you go back to the cloudy model plot?
This one.
Yeah, so I'm actually kind of curious because this means that none of the model, except the shock model, the star formation or the quasar cannot explain all the type 2.
Yeah. They shouldn't explain because these are AGN and then the stars are stars. Yeah.
I'm just curious, have you explored just playing around the model to see whether or not, for example, if you just assume it's a star formation, but somehow the galaxy can produce harder radiation, whether or not you can actually pushing down the line a little bit. I mean, for the star formation.
Yeah, there's a paper that what in the model they do is they have the host galaxy and then they start to introduce like say 50% of AGN, 80% of AGN, 99% AGN to see where the contribution or the dots, the models goes. I think it's investment plate 2019. They have done this kind of thing that they have a model grid and using the same abundance of the galaxy abundance have to be the same for host and the agent, although it doesn't have to. And then they see the contribution of shocks and AGNs and like X-ray binary in the host galaxy to see how the line move. In this one, the model that I have, I cannot just simply add them together and then see the contribution because you might have like ionizing parameter for the host galaxy equals to 10 to the minus 2, but then the ionizing parameter for the agent is higher, so then end up with for one galaxy you end up with different type of contribution of like AGN, and the direction is going to be going down because like the distribution, but then I simply just didn't plot it. I was also saying that some papers that is our cooperator have done that, and you can take a look at it.
Any other questions?
Or maybe about like Minnesota.
Okay, if none, let's say the video again.